Good to go.
All right, everyone, welcome. Today we have MLOps Engineer Chris Thompson to show us how easy it is to go from idea to production using Vertex AI on the Google Cloud platform. So thank you for being here and take it away.
All right, thanks, Regina. So some of you may have been here the last time that I was here talking about MLOps, and we did sort of a high-level overview. And if you would like to see that, I know they did a recording of it, so it's worth a watch to kind of put this into context. What I'm about to show you, for just for those who weren't, I made a kind of a reduced version of my last presentation, so that we can kind of get up to speed and be on the same page when we start talking about this stuff. Okay, so we'll start out with a quote, right? No machine learning model is valuable unless it's deployed to production. And that's the crux of MLOps, right? Is how do we get models into production? What does that look like? And, you know, it's seeming, and it was at the beginning, this was something that companies thought, you know, oh, we'll use traditional deployment patterns and put models into production, and that should be fine, right? We know how to do this. We've been doing this for decades. And they started experiencing lots of weirdness, and we're going to look into what that weirdness is or what it might be, right? And why we need kind of a different pattern or some enhanced patterns, let's say, when we are deploying models into production. Okay, so we'll go through why MLOps. We'll say what MLOps actually is, because, you know, that may not be a term that everyone's familiar with. We'll look at the components of MLOps. I'm going to zoom through this pretty quick, and then I want to get to a demo. I want to show you what it might look like, right? We're going to look at code today. For those of you that aren't familiar with Python or haven't done much coding, that's okay. Just follow along with me. I'll explain what each part is doing on a high level, right? But for those of you that are familiar, definitely take note of this stuff. We're going to mention some technologies that are going to be really useful, maybe in your day-to-day if you are dealing with machine learning in your job or even in, you know, personal projects and stuff. Okay, so starting with why MLOps, right? So what is machine learning? And machine learning, defined by Wikipedia, which I grabbed, and Wikipedia is always right. So the study of computer algorithms that can improve automatically through experience and by the use of data. Algorithms build a model based on sample data known as training data in order to make predictions or decisions without being explicitly programmed to do so, right? So that's the learning part. So, you know, machine learning is a bunch of algorithms. It's not one, but there's a bunch of different techniques. But the idea is that you give it some data and it can learn attributes about that data algorithmically, right? And kind of build itself, right? Build its own idea or model about the state of the world based on the information that it's given through the training data that's provided. And this is one of my favorite gifts, right? So it says, this is your machine learning system. And he says, yep, pour the data into this big pile of linear algebra and collect the answers on the other side. And he's like, what if the answers are wrong? And it says, well, just stir the pile until it starts looking right, right? And this is kind of points to some of the criticisms of machine learning, right? In that we can get, and this is statistics in general, right? Which is part of the backbone of machine learning, along with linear algebra. And in statistics, you know, you can really manipulate it to tell you whatever you want, right? And the same is true of machine learning. That carries through, right? So there's techniques on how to get around that, but it's something to keep in mind about machine learning is it's not an unbiased process, right? There's a human element of bias that is injected into every single model that is trained. And so take everything you see, including things like recently the sentient AI, right? Take all of this with a grain of salt, because there's a lot of human interaction that happens just to get the model into a state where we see the end state, right? And so don't believe everything you read. So we have an MLOps process. So the machine learning life cycle, right, goes like this. You define a business goal, right? You always need a goal, something you're trying to solve. You access and understand and clean the data. So you get some data that you think might answer your problem from a SQL database, or you're collecting it from humans or whatever, right? And we clean that data, we process it, building things called features, right? We call them features, which are the food that our ML model wants to consume, right? So we have to, an ML model can't just take any data, right? It has to take it in a certain form, and so we manipulate data to put it in the form that a model might accept. It's different for every model, right? But that's the basic process. And then we build our model based around our problem that we're trying to solve. So maybe it's a regression problem where you're trying to predict a number, right? So you're predicting housing prices or something along those lines, right? So you're using a regression model versus, say, a classification model. We might use a logistic regression, or even for both of those, you could even use some deep learning methods, right? Which we've all heard about. And then we deploy the machine learning model. Things happen, we observe what happens, and then maybe we need to do something different. But in the end, we iterate. So this is a cycle, right, of constantly redefining our goals, cleaning data, building models, evaluating models, and so forth. So a lot of people, when data science came out and in general, are very interested in building models, right? But that's actually a really, really small part. This is a very popular image that you'll see posted all over the internet. It comes from Google, right? And it was actually adapted from a paper called The Hidden Technical Debt in Machine Learning Systems. It came out in 2018, I believe. And this was the first time people were like, yo, it's not just about building models, right? We really need to, there's a whole other part to this, right? With applications, it's not just writing an application, right? There's infrastructure involved, there's testing involved, there's all this kind of stuff. And so same with ML. So writing the ML code is actually a very, very small part of the process. And the rest is all that you see around it, right? And so you can see where we start to need patterns, right? To make sure that all of these things are being taken care of in a way that makes sense. And these things would be unique to machine learning models, right? Like I said, there's plenty of processes for developing, testing, and deploying application code, but ML models are different. And we'll talk about why that might be. And the reason we need MLOps is, this chart shows the percentage of time that data scientists are spending, right, just getting ML models into production, right? So we see 36% of participants said their data scientists spend a quarter of their time. 36% said their data scientists spend half of their time. 20% said they spend half to 3/4 of their time, and 7% said their data scientists spend more than 3/4 of their time deploying ML models, which goes to show you just how complex and difficult this problem might be, right? And how time consuming it is. And a data scientist is someone who's very valuable, right? You've seen the salaries, right? They pay these people tons of money to do this. And the last thing they want them spending their time on are engineering problems, right? DevOps problems, because these people get paid to look at data, to build models. That is why they're there. So if they're spending 36% of their time just getting the model out there for end users, like that's a problem, right? Because that's not technically what they're supposed to be doing or why they're being paid. And so that's where we get MLOps, right? Like this idea of we need a separate position or a separate set of skills that can deploy these models, right? And we talk about 4 key reasons for MLOps, besides the fact that data scientists are expensive. We don't want them spending their time doing this, right? There's a lot of dependencies. So the data in the business are constantly changing. That means there needs to be, communication in order to ensure the model that's in production, right, aligns with the expectations of the business. So the business expects things from that model. And if that model starts producing things the business doesn't care about or solving a problem that's not valuable to the business, we need something different, right? We need to redefine those expectations, right? We need to address that original problem that we cited when we were citing our business goals and risk mitigation, right? So deploying models is risky. Why is it risky? Because the world changes constantly. And when we're getting real-time data from the world, right? Well, that model isn't changing based on the world. Once you train a model, it's a static graph or a static model, right? And so it doesn't change with the world. So if the world changes, that means we need our model changing with that world, right? Or that state of the world, and keeping in sync with that. So this is where monitoring comes in. So we need to monitor our models to make sure that they are in fact keeping pace with the rate of change in the world. we have responsible AI, right? And this is made up of two main aspects, right? So intentionality, right? So we want to take into account bias in our models, like I was talking about earlier. When a human trains a model, right? We've seen this with a lot of like models that are, say, predicting some health problems, right? Well, if you only take it from a certain segment of the population, let's say it was, we just looked at, certain income class or even a certain race, right? That doesn't account for these other people, right? So we don't actually get an accurate model for the general population. We get it for a very specific segment of the population. Now, it may be the case that you have multiple models for different segments, depending, right? But overall, what you want is to keep that in mind when you're building a model. So responsible AI includes bias and accountability, right? So data as it's traveling, right? That it's handled and collected responsibly. And, there are apps, all sorts of apps and different things that we've all probably heard about that include or apps that are tracking us, right? And the question is, is that being done responsibly? And this is always up for debate, but it's something to keep in mind when you're building a model and collecting data. Are you doing it in a responsible way, in a way that's fair and let's say legal, right? Especially with sensitive information like health data and so forth. So scale is another thing. So being able to deploy your models, right? So if you deploy one model, great, but like if I have to deploy that onto some compute, right? It takes resources to host that model. Well, if my model starts getting hammered, right? Because more people are using my application that has my model in it, right? We're going to need to figure out how to scale that model. And while it sounds easy, that's not necessarily the case, right? Like being able to direct traffic to the right place and make sure that all users are experiencing or getting the same experience when using my app or my API that is connected to my model. That's important. It's a hard problem to solve, right? And it's not totally solved yet, right? But there are plenty of companies doing it at scale. You think of the Googles, the Microsofts, the LinkedIns of the world, Facebook, and so forth, Twitter. Okay. So what is MLOps, right? So we're still not quite there, but let's answer it. So MLOps is a set of practices that aims to deploy and maintain machine learning models in production. It seeks to increase automation, improve the quality of production models, also while focusing on business and regulatory requirements, right? So we basically just built up to that definition. So that should sound, kind of redundant from what we've already discussed. And it's the collision of data engineering, machine learning, and DevOps. So it's like this conglomeration of all of those practices. It borrows a little from everything to coordinate these models in production. And so this is what like an early or immature MLOps solution might look like, right? We get we have some offline data. Let's say it's sitting in a SQL database. We extract and analyze it. We prepare it. We maybe pre-process it for feature engineering, right? We feed those features into model. We evaluate model, and if we're happy, then we just out the other end gets a trained model, goes into a model registry. That's just some kind of storage to store your model, which you can think of as nothing but some files that represent a model, right? And then we deploy that for serving, and we have our prediction service. But notice there's no loops. Like, remember we said it's an iterative process. No loops. This is a linear pattern, right? And so why would we want loops? Well, we have things like concept drift. So concept drift is the idea that, say we have some inputs coming into our model, and Y is what we're trying to predict. In this case, you can think about it as housing prices, right? So if we input X, right, we expect Y, and our model is stuck at that state, right? But in 2020, housing prices and beyond to today, housing prices went through the roof, right? Like they went crazy. So if we were still using that model that we trained in 2019, right, it's not accurate. It's not consistent with the state of the world today. And so this is the idea of concept drift, that the relationship between our X's, our inputs, and our Y's, our output, has changed, and we need the model to be retrained or trained to understand those differences. What else? Data drift, right? So it could be the fact that our relationship might be similar, but our X's have changed, right? And this is an example here. So pre-pandemic, people were doing 5 transactions a day at the ATM, and we have a model that say is trying to predict fraud, right? And it says, okay, on average, 5 transactions every day. That seems right to me, right? But then pandemic hits, all of a sudden people are doing 7+ transactions a day, and it's saying that's outside of that average that I was expecting, and therefore I'm going to flag it as fraud. When in fact it wasn't fraud, it's just that the distribution of our X's, our inputs, had changed. The state of the world again had changed, right? And we need to account for that in our model. And this is why we need that cycle of retraining, right? And other things can go wrong. There's other things to consider, I should say. So not related to data. Will your model serve batch or online predictions? So are you sending predictions all at once, or is there a steady stream of predictions constantly hitting your model, right? Where will your model be deployed, right? We're talking bare metal, which is like servers in a data center, or the cloud. We're all familiar with the cloud at this point, I think, Google Cloud and AWS and so forth. IoT, so it could be on the edge somewhere on some sensor living in some manufacturing plant. You can do it straight in the browser with Java or TensorFlow.js and things like that, which is super cool. And there's other places, right? And also, does the model need access to the internet? So they call them oracles, right? So an oracle is something that gets data from an external source so that the model can have that data, because the model can't itself connect to the internet, right? So we need some way to give the model some information from another location that might be somewhere on the web. Okay, and so the components of MLOps become much more complex when we have a robust solution, right? So we have a place to keep features. Maybe we don't want to recompute features all the time. We just want a place where our data scientists can go to take features, and so that eliminates that process of constantly having to recompute the same features all the time, right? So we'll start. Where do we start? We want to start. All right, let's start at our feature store, right? Okay, so we go to the data scientists will have an experiment that they want to do. They do some analysis on the model, and this might be a back and forth in here for a while, right? And then they finally get it done, and they have their code. Their code goes into a source repository. Think Git, GitLab, GitHub, so forth. And then there's a CI process, a continuous integration process. Now, notice that this borrows heavily from DevOps, right? And so we go to packages. It builds a package from these components and deploys a pipeline, right? So we'll look at an example of a pipeline in the code that I have. And that pipeline, right, that automated pipeline deployment extracts the data, validates the data to make sure the data is in the correct state that we want it to be in, prepares the data in some way, some sort of pre-processing or something, a model training, right? And the reason we want a data preparation step and all of this kind of stuff is so in the real world, our steps are exactly the same as they were when we were experimenting, right? So if we built something here, we need that replicated for real world, right? We need that to be the same every single time, those steps, right? So we want those to be static steps that happen the same way on the same data every single time. And so we have data preparation, model training, right? We evaluate the model, make sure it's correct and doing what we expect it to do. We validate the model, and then we put it in the model registry, right? And so in this step, we're actually saying, hey, is the model better than the last model that we built? Because if it's not better based on our criteria that we've done, right, or we've defined, then why would we deploy it, right? Just keep the same model that's already sitting out there. That doesn't make any sense, right? So, okay. So we put it in a model registry. Think of source code repository. It's not, but think about it as that. So it's a place to store our model files, right? We deploy that trained model on some sort of serving platform, and we'll show a serving platform today, but there's other examples like the NVIDIA Triton server is a very popular choice for deploying deep learning models into production. And then people can, once we have it as an API, then we can make predictions against it. So we're making predictions, we're making predictions, we're making predictions. At the same time we're making predictions, we're monitoring that performance on real live predictions, right? So is it still doing the right thing? Is it still doing the right thing? Well, once it's not doing the right thing, once the performance drops in terms of predictions, you're like, okay, we need to retrain. That should trigger a retraining, right? There's also sort of a cron job style where you do it every, say, 2 weeks, right? You just know I'm getting a certain amount of data every 2 weeks, and I'll retrain it on that data once I get that data, right? So there's also that. But performance monitoring is key, because what if your model breaks down within that 2 weeks, right? You need to know that. And so then you have a trigger that triggers the retraining process, and we go back and we do the same thing over and over and over and over and over, right? So this is a very robust system, okay? Let me see, is that the end? Yes, and that's the end of my slides for that. So we're gonna move on to code, okay? And we'll have time for questions for sure. I just wanna make sure we get to the fun part, right? The code. Okay. Scroll all the way back up here. Okay, so am I still, let me reshare my screen here. So I'll stop presenting. Present. Collaboratory. Okay, so you should be seeing, okay, cool. So this is a notebook, okay, a Jupyter notebook. Many of you who are familiar with Python or data science have probably used Jupyter notebooks. For those who aren't, it's just a, I didn't think to explain it. It's a place to experiment, right? Run code. It's not meant necessarily for production type applications, but it's a place where you can, an isolated environment to be able to experiment, run code, try things out, maybe do some training, that kind of thing, right? In terms of machine learning in general, some people use it to experiment in general with Python and application. But it's nice because this is a managed version. This is called Collaboratory. It's on Google, and I'll drop a link for that later unless someone can find it. So Collaboratory is a managed version. It comes with pre-installed with all these data science packages, because a lot of times it's really annoying to get all the packages you want, right? So this comes with TensorFlow installed. It comes with NumPy installed. It comes with Pandas installed. It comes with all the goodies, right? So it's a really easy way to just like get started without needing to worry about all of the dependencies that you need. So what we're going to be doing today is we're going to be doing what's called fine tuning, and we're fine tuning a BERT model, okay? And so this is the original kind of transformers model. It's a natural language model, and it came out in, I believe it was 2018, that BERT was released. And there's been many, many, many iterations now that are much more powerful than BERT. But originally, this blew people's minds, right? The transformer model is an amazingly powerful model and kind of changed the game on natural language processing. Okay, so with this natural language processing model, this BERT model, we're going to be doing a very classic solving a classic problem, which is using sentiment analysis on a movie data set, right? So it'll be able to take some movie reviews and classify them as positive or negative, right? And we're not going to go too deep into what it's doing in the background or whatever. There's tons of tutorials online, and that's why I chose it, because we don't want to concentrate on that. We're concentrating on the MLOps portion of things, right? And so I'll also share this notebook link after we're done. Okay, so we're gonna download a data set, right? We're gonna create a data set, a validation data set and a training data set. The training data set is for training the model. The validation set is for evaluating the model. We're gonna fine tune the BERT model. Now in a deep learning model, there's things called layers, right? So the BERT deep learning model has been trained on so much data, like a lot of data, right? And so but what we can do is we can actually borrow all the low-level features that it learned and just train that final layer, which is the highest level in the network or the deep learning model, right? And when we fine tune it, we can fine tune it to a task that we are doing. So we're utilizing what Google did for training this model, which takes a very long time. And we can skip that and kind of piggyback off of that to tailor it to what we needed to do, which is classify movie reviews, which was not the original intent necessarily. BERT can also do things like question and answering, text prediction, language translation, and so forth. And you can fine tune it to do those particular tasks. Okay, so it's very versatile. Okay, so we have this Cloud Notebook. All we're doing here is we're going to do some installations, right? So we install, and all it's doing is so I said it's installed, it has a bunch of things already installed, but some of the things are not. And so we're just installing the things that we didn't actually have before. Okay. We run this. So what I'm doing here is called running cells. And so each of these cells will run this piece of code, right? And so you can already kind of see why this would be useful, right? I can isolate different chunks of code and run them in any order of really that I want. In this case, we're running top to bottom, but each cell only depends on what's already been run, right? So like if I run something that needs a dependency that hasn't been, and we didn't run these installs, it wouldn't work, right? And so we want to run these in order. So we do that. We're going to define some constants here. This is a project ID. That is a GCP resource, right? And within GCP, a project is nothing but a place that's attached, or an environment that's attached to a billing account, right? And that allows you to like actually do things in the cloud, right? So a project is nothing but an area that you can work on in Google Cloud that has some sort of billing attached to it. All right. So we set our project ID. I have a project already spun up, just so you know, but you would need to create one and plug that in here. We're going to define a timestamp. Timestamps are a great way to track artifacts that are created out of your MLOps processes, right? So if I have a model and I have, there's other things that can be produced from this, like let me think, like confusion matrices or rock curves, which are things that you use to evaluate a model. If you want to tie all those together, a great way to do it is through a timestamp. So you use the timestamp basically to say, okay, on today at what time is it? I don't know, 1:30, right? The model that was trained at 1:30 is tied to this graph that we're keeping over here, and maybe this data that we're keeping over there, and it keeps everything connected when you're storing it across different places, right? And so we use timestamps liberally when we're doing data science, or you should, or you can't. All right, we define a region. Now, GCP regions, right? I'm not going to get too deep into GCP. It's just a location where a data center is located. And for more info on GCP, I also did a talk on GCP that kind of deep dives more into what GCP is, what the cloud is, all that kind of stuff, also on Tech Academy's YouTube channel. So definitely check that out if you're interested in learning more about that. All right, so here, I don't define a bucket name. The logic here basically creates one for me. And a bucket is nothing but a place. It's called blob storage. We can store any kind of file we want as long as it's made up of bytes, right? So videos, text files, JSON, any type of file you want, right? Okay. And it's basically unlimited. Okay, make sure our bucket got created. It did. Okay, I'm using a service account. A service account gives permissions to an application, not a user. So I'm a user, right? So on GCP, I have permissions, but an application maybe needs permissions to do stuff in GCP too. So here we're using this service account to grant our pipeline permissions to do things in the cloud, right? So we do that. Okay, now we're down to, well, hold on, let me grant some more. That's the permissions. Okay, so now we're down to the actual the pipelining part, right? So we defined some of our installs that we did earlier. Here we're using Google AI platform. So Google Vertex AI, all Google resources and APIs have a Python library attached to them, so an SDK, and you can use that, right, to interact with Google Cloud. So you can build Python applications that interact with Google Cloud, and Google built these packages to make it really easy, right, to authenticate and use Google Cloud services from Python, and maybe your Python applications, or in this case, our Jupyter notebook. Okay. So here we choose a BERT model. Now notice there's lots and lots of iterations of BERT models, okay? Like I said, this has been around a very, very long time. because we're doing this fine tuning, I chose the smallest BERT model, and models in terms of deep learning are defined by layers, number of layers in a model, and number of nodes within a layer, right? And so the larger those are, the more information the model has, and the more the larger the file that's produced from the model will be, right? And the longer it takes to train that model. That's the main goal here. So I don't want to sit here for 6 hours and wait for this model to train. So we are going to choose the smallest one. And really, we're not even going to wait for the 20 minutes that it takes to train. I already have one trained up, but we'll go through the process nevertheless. One thing I wanted to mention about Colab notebooks is if you come to change runtime type, you can actually, it gives you a free GPU and TPU. So a GPU is a graphical processing unit. TPU is a tensor processing unit. And both of those, a GPU is more generalized. It performs very quick matrix operations, which is needed in gaming, but also happens to be needed in machine learning, right? So you can use a GPU to optimize your training times for your models. Instead of a CPU, it takes much more time. And a TPU is specific to deep learning, was developed by Google, and that is really decreases the time of your tensor or your deep learning models, right? We're not going to actually use the built-in TPU. We're going to do everything on the cloud, but nevertheless, it's available here. If you want to experiment with deep learning, it's a great environment to do it. It's free, right? Okay, so on Google Cloud, we're going to define our training and production compute. So here we're using the same thing. We're using what's called an NVIDIA Tesla K80. It's a GPU. It's very cheap, good for most use cases. You know, it's the fact that it's inexpensive is why I'm using it. My company probably wouldn't like it if I used like an A100 or something, but there are tons of different GPU types that you can experiment with on Google Cloud. So if you are on there and you're doing experiments, definitely check those out and tailor it to your needs. Okay, we define our TensorFlow type here. We're using 2.3 for compatibility reasons. We define our compute. So I said we're defining our compute above. That was the GPU. Here we're just defining our CPU and our machine type. So there's machine types on Google Cloud. Here we're going to be using 16 vCPUs for training because we have some pre-processing that we need to do, which is compute intensive, right? So we're going to use that type for the training / pre-processing portion. And then we're going to use 4 vCPUs for deployment because our model is going to be deployed on a GPU. Therefore, we don't need a lot of CPU power to be able to, our process is not CPU bound. It sort of is, but it's utilizing the GPU. So we don't really care that much about the CPU in this instance. All right, here we go. Okay, so we initialize all of our, the client to be able to talk to Vertex AI. And here's where we get to the actual, like the pipelining. So we've defined a bunch of constants up above nothing's been built yet, by the way. Absolutely nothing has been done. We're literally just mapping out and defining what we want to happen, right? So here we define this thing called a component. What's a component? Well, we're utilizing a library called, it's called Kubeflow pipelines, but it's managed in the cloud on Google Cloud. So it's called actually Vertex AI pipelines. Vertex AI pipelines is built on top of utilizes Kubeflow pipelines. And what is Kubeflow pipelines? Kubeflow pipelines is a pipelining library that allows you to coordinate machine learning like the MLOps process, right? So you might have some, like we saw in those steps, a pre-processing step. You might have, evaluation step. Then you might have your model training, and then your evaluation of the model, and then your deployment, right? So it coordinates all those steps and allows you to do this kind of logical grouping of things where you'll see, and we'll show the visualization of this in just a second, where it turns into what's called a DAG, a directed acyclic graph. So it all information flows in one direction. It can go in different branches, but it's all moving in one direction. And if you've ever worked with something like Apache Airflow or anything like that, you'll know what a DAG is, right? And actually, anyway, I don't want to get too deep into that. So I have defined a function here. Now, this seems like a lot of code, right? You're like, oh my God, we're not going to go through this. Okay, but just know what it's doing, right? The main idea is that we've got, we're downloading our data set, okay, which we do in the beginning. That could be optimized. We could already have our data set stored and just be pulling the data. This is a demo, so we're just, downloading the data every time we run this. We pre-process the data, right? We turn it into a training, test, and validation set, right? And then we actually build the model. That's what this code is doing, building the model, right? We define our loss function. Okay, let's not get into loss functions. This is all deep learning stuff, TensorFlow stuff. There's plenty of resources on that. If you want to learn that, definitely definitely encourage you to do that. But we're not going to deep dive that here. And then we end up, this is what actually trains our model. We evaluate our model, and then we save our model. Okay, so this is just a function. All right, it's a Python function that does that stuff. And we can break for a question if you want. Yeah.
Is it okay if we make it a little bit bigger? Is there a way to do that?
Oh, yeah, totally. I'm sorry. Yeah, let's pull that up. How's that? Better?
Let's see. Sure. Is that better? Okay, better. Thank you.
Better. Okay, cool. Yeah, no problem. Oh no, that's terrible. All right. Well, anyway, yeah, let me know if I need to make it bigger. I can always make it bigger. In fact, I will, just for good measure. There you go. All right. So we save our model, right? So that's all it does. Pulls the data, pre-processes data, trains model on data, right? And then evaluates model, saves model files out. Okay, so 5 steps in this one function. Really, we could break that into multiple functions, create multiple components, that kind of thing. I would encourage you to do that. Again, this is a demo, so I didn't want to have too much complexity in this. So we do it all in one function. But if you take this notebook and you end up copying it, I encourage you to go explore it and do that yourself, because it is very valuable to do those types of exercises and understand really what's happening under the hood. All right, so we have what we do here is we're creating, so in pipelines, you have these things called ops, okay, operations, ops, right? So each step in the pipeline is an op, okay? So here we're creating our training op, and we create that from our function that we defined up here, custom train model, okay? And we define our compute that we defined, our GPU we defined, and the number of GPUs we want, right? We defined all of that up above, so we're just actually utilizing those here, okay? Now, we get down to the pipeline. We define the actual pipeline. We've defined some components for the pipeline. Now we need to define our actual pipeline, okay? So here we're going to do what we set up above. Obtain the data set, train custom BERT model. Now, there's some other, that's one step, right? That's that function we put above. That step does that part, but we have these other steps. We take that model, we're going to upload it to Vertex AI. We're going to create a Vertex AI endpoint. So an endpoint meaning a place where we can send traffic or send requests to our model. So you need some sort of interface, right, to accept requests. A model in and of itself doesn't accept like HTTP, right, which is why we need a model server. Okay, and a model server will wrap that in an API so that we can send it HTTP requests or other types of requests, but we'll just go with HTTP for now, right? And so you need to create an endpoint, and then you deploy the model. Notice the, notice the capitalization here, right? These are actual GCP resources, okay? But all that is deploying the model to that API endpoint to allow it to accept requests. Now, we don't actually have to do anything. Since we're using TensorFlow, and there's several other libraries that are natively accepted by GCP, GCP just knows, oh, this is a TensorFlow model, and it handles everything for you, right? You don't have to know anything except what the inputs of your model are, okay? And we're going to see how this all seems very complex. Again, I'm going to show it in GCP, and you'll see oh, I get it. That's pretty straightforward, right? It's a lot of code just to do this very simple thing, but it's worth it, right? There's lots of customization you can do here. Now, some people don't like that. I work with a lot of custom type models and coordination of those. And so to me, this is not too much. I like having the flexibility to do what I want, right? But utilizing GCP does handle all of the infrastructure type stuff behind the scenes. So all you really need to do is give it a model and it handles the rest, right? Okay, so here we're actually defining the pipeline. So notice we name our pipeline, okay? We define some constants up here that are just utilized. And notice we're utilizing that timestamp, right? Which will let us track resources, which resources were created when, right? So we use that constant timestamp to make sure that when the model is created, when the endpoint is created, that all of those are connected via that timestamp. All right, so now in here is where we utilize our ops, okay? So here's our custom job op we created above. Give it some inputs. These are the inputs to the function that we created. Okay, so this will be one node in our pipeline. This is connected to that, right? So it defines, you can define some specs for your, now it's good to note that when models run on Vertex AI pipelines, they're actually running as containers on a Kubernetes cluster. Again, you don't have to really know much about that, right? All the Kubernetes magic happens automatically for you, but it's good to just keep that in mind. All right, so we upload the model. So here's where we upload the model and create a capital M model resource in GCP. Okay, so it's basically taking that container, right, and turning it into a resource that Vertex AI can utilize wherever it needs to within the GCP environment. We create an endpoint. That's the endpoint we were talking about, right? So that's another node in our pipeline, which we'll see in a sec. And then we have our model deploy operation, which actually deploys the model to the endpoint. And we can say a traffic split here. So that's something interesting to note, right? So right now we have it set to 100. So every new model that gets deployed gets 100% of the traffic, right? But maybe that's not ideal. Maybe we don't want that. Maybe we want it to only have 50% or 20% of the traffic. So you can do what's called a canary deployment, right? Where you have a subset of your requests coming in and going to one model, right? So you say 20% of my requests will go to one model, while the other 80% will go to the other model. So you're kind of testing the model in production on live data to see if it works, right? And if it does, then you can, crank it up to 100% and divert all requests over to that. Now, if it starts failing, you can also revert back, send 100% of the requests back to the other model while you fix that one. Right? So there's lots of good features here that we can utilize that are very easy. Whereas if you were doing this, coordinating all of this by yourself, right? Or I should say manually, not as easy, not as fun to figure out, right? Okay. I'm going to scroll up for a second because I have a bad habit when I'm doing these things of not running my cells, and then we run into errors because it doesn't understand what I'm trying to do. All right, there we go. Okay, we're caught up. All right, so we come to this step. It's called a compilation step, a compiler, right? And the compiler, what it does is it takes your Python code, all of this Python code that we wrote, right? Well, remember I said that the pipeline is going to run on Kubernetes? Kubernetes doesn't inherently understand Python, right? But what it does understand is YAML. YAML is the native, call it a language, that you write your configuration files for in Kubernetes. So what this compilation step will actually do is turn your Python code, all of the things we defined up here, right? Remember, we haven't run anything yet. We've just merely been defining things. This is the step where something actually happens. It takes that code and it knows how to turn it into Kubernetes files, right? YAML files that Kubernetes understands, which is really sick because you don't have to write those YAML files. You just need to know Python and you just let AI pipelines handle that part of it, right? Kubeflow pipelines, but again, right, we're working Vertex AI, so it's called Vertex AI pipelines. But nevertheless, that's what this compilation step does. You'll notice JSON and YAML are interchangeable. This could easily be YAML. We have JSON defined here, but YAML is like a more readable version of JSON. Just think about it like that. They're actually interchangeable, and there's compilers that will turn JSON into YAML and back and forth. But that is neither here nor there. We run that. Okay, down here, this is where we actually run the pipeline, and then we get to go see it working on the cloud. That's the fun part. Okay, so we've defined all that stuff. we define some metadata here, display name, our template path, which is the template that the compiler creates for us, right? So you see, we named it here, so we put it here. This replace step, don't worry about this. This was just it doesn't understand, right? Spaces, or I forget what it actually even was here. There was something wrong with it. Anyway, that's just a step we need to make sure it's compatible. The naming convention, it complains at you. There's lots of little nuances here. But anyway, let's run it. I don't need to get into that. So you notice created pipeline job. So we have our pipeline job running. And so what we'll do is we'll click on that link that it provided. And now we're in Google Cloud Console. And here is our pipeline, right? Each of these is an op that is doing a unit of work that we defined the op to do, right? So here is our custom trained model, okay? This is working, right? And we can actually view the logs. Right now it's waiting for the job to be provisioned, but it will be provisioned and then training will commence, right? So we can actually view the logs from this viewer, right? We can go look at the endpoint. Now, one thing I didn't note, and let's come back to our notebook real quick. I just wanted to show you something that's interesting and really, really nice. So we'll go, here's one. So we have, go back down. Get that out of the way. All right. Okay. So we have this model upload op dot after, okay, custom job op. So what that does is you can actually define the order of operations that your pipeline runs in. So what this is saying is, well, we don't want to upload the model. Where are we? We don't want to upload the model until the model's trained, because you don't have a model, right? Until it's trained. So it's saying don't run that particular step until after this step, right? And similarly, I think we have one more, maybe not. Okay, maybe I just have one in here. But we can come back here and we can notice that, right? So the custom train model, the training of the model happens first. Notice model upload has not done anything yet. It's waiting for a successful completion of that step, right? And then, and let me zoom in here. I remember people were, all right. And then, but notice the endpoint. The endpoint's already created. And the reason we can create the endpoint is because it's not really dependent on anything and nothing is affected by it, right? We in fact want the endpoint created, right? And really the model upload should maybe be connected to the endpoint create as well. But we know the endpoint's probably going to get created before this. There's ways to like define multiple, right, steps. So wait until this step and this step are completed. That would probably be logical, and I should probably do that. But nevertheless, you get the idea. We can control the flow of our DAG. So this is a DAG, a directed acyclic graph. Notice things flow top to bottom, one direction, acyclical, right? There's no cycles in this graph. And the last step we have will be the actual deployment step, which notice we defined here. Okay, I did do it. So the model deploy step actually does depend on both the model upload and the endpoint being created, right? So it's not going to deploy unless we have an endpoint to deploy to and a model to upload, or a model upload completed. Okay, so we're talking about all this stuff like model uploads and stuff. Well, we can go check those out, right? So here's our endpoints. Okay, and we see that we have this endpoint that was created. And notice this timestamp at the end, 2022, 06, 24, 20, 30, 51. Or sorry, did I say that wrong? 624. Well, anyway, you get the idea. So whatever the time was, that I think it's on Central Time, so that's why it's at 30:51 instead of like 00:51, right? So 3 hours ahead, or something like that, or 1:51, or 2 hours ahead. Sorry, Central Time. There you go. So it's in Central Time. Notice that we defined our region to be Central Time, so it's actually in Central Time. I could have set that to Pacific Time or whatever I wanted, but nevertheless, we have our timestamps. So our endpoint's ready. Now this will take a while to.
Hey, Chris.
Succeed. Yes.
Sorry to interrupt, but is there a way to actually make this also a little bit bigger?
Oh, which one? The
when you were showing the timestamps.
The endpoints. Yeah. Let's do that. Thank you. There we go. All right. Oh, wait. Are we in the right place? Oh, yeah, right here. Okay, everything got a little crunched. All right. So here's our timestamp here, if that's big enough, so we can make it bigger. So 2022 06 24, right? And then what is it? 203. Okay. Well, regardless, this is the timestamp here, right? And so you can see that we can link things by these timestamps, right? And our pipeline is going to take a while to complete, so we're not going to wait for it to complete. And lucky for you, I already completed. So one earlier. So we can take our endpoint. So what we're going to do is each endpoint it has an endpoint ID attached to it, right? So we take that endpoint ID. When we come back to our notebook, and we can stop this. And let me just double check that our model also built. Or I could have clicked into the endpoint, I suppose. Let's go. Let's do that. Model, fine-tune endpoint. All right, here we go. And here's our model that's deployed. That is also ready. Great. Okay, just double checking that we're not going to get some errors here. Always good to double check yourself. Don't get cocky. All right, so we'll take that, right? And we go back to our notebook. And we stopped our training pipeline. Again, I already made one earlier. So here is where you put that endpoint ID. So we define our endpoint ID. And actually, I can put it here. I keep doing it there because I'm used to code. I have these little input boxes. There's lots of different cool little like widgets that you can add to Collab that are built in. And you use this kind of like comment at param style to define those. So here we can input it into this box and notice that it auto populates over here. Okay, so we need to run that. Okay, cool. And now what we're going to do, okay, make sure that that's correct. All right, if that runs, then you're good. No errors. Okay, so what we're going to do is we're going to give it some movie reviews. So remember, the whole point of this was to train it on movie reviews to get some sentiment analysis, right? Now, sentiment analysis is between a positive and a negative number. I do know the scaling on this is a little weird. Usually it's +1 and -1. Here, I think it's +4 and -4, but the idea is the same, where the closer you are to the positive number, the positive maximum, right? Or positive maximum, the maximum, right? The more positive the sentiment. The more negative towards the negative side it is, the more negative the sentiment is. And so it'll tell us that, and obviously with 0 being neutral. And so we have, this is an amazing movie. This movie was great. This movie was meh. This movie was okay-ish. This movie was terrible. We're going to send those to our model. And what we should see are some predictions. So here we go. These are our raw predictions that we get from the model. Now let's match them with the movie reviews. They're in order. So we get, this is such an amazing movie. That's very positive. Almost 4, right? Movie was great. A little less, still very positive. Movie was meh. Look how close to 0 that's getting. Look at that large drop there. That means the sentiment was like, yeah, and then the movie was okay-ish is even, maybe even, yeah, it's less, it's more just like in the middle, right? Closer to the middle. Now the movie was, or did I mess that up? No, I'm right. Okay. And then on the very bottom, we have that movie was terrible. Look how negative that number is. Now these should be scaled, but I failed to scale them. What are you going to do? But the idea is there, right? That the sentiment is based on the magnitude of the positive or negative, right? So again, the more positive the number, the more positive the sentiment, more negative the number, more negative the sentiment. So we see that our endpoint is working. That is wonderful, right? Like that's exactly what we're looking for. Now, you may be thinking about like, okay, how do you turn this into a cycle, right? Well, there's lots of other things we could do in Vertex. I'm not going to do them right now. I just wanted to show you that part of it. But we have, here's where our, say, feature store is, right? So we can load features from here. Remember, we were talking about the feature store to speed up, right, the experimentation for our data scientists. We have data sets. We can store data sets here, right? And we can even experiment here, run experiments. We can get visualized outputs using things like TensorBoard and Vizier for hyperparameter tuning. If you don't know what that is, no worries. But tracking all of this stuff, and we can use metadata the metadata of the endpoint to actually do the monitoring we were talking about. So we can decide if the model was better than the last one. We can decide if and be monitoring our model to see if we need retraining, like all of this kind of stuff. And so this is really, really powerful. And the metadata store, remember I said we can use timestamps. Well, the metadata store is another way to track what that model is attached to, right? So it keeps an object in here of, right, all these artifacts, and they all have metadata attached to them. So it tells you created this time, last modified this time, the resource name, all of this stuff, and they can come as JSON objects. So you can actually use those JSON objects to monitor and do whatever you need, retrain, rerun pipelines, track experiments, all of that stuff. And that's all done within Vertex AI. So that is as far as I want to go. There's lots more to explore. Hopefully that was very cool, seeing a model be trained in real time and kind of understanding and being able to match that process to a lot of the MLOps stuff that we talked about at the beginning. But I'm happy to take any questions if there are any questions. I see there's already a question.
Well,
probably lots of questions.
I'll let listeners know they can put their questions in the chat. If you do want a verbal question, I can unmute the mics. Just raise your hand.
All right. We can honestly start from that one with Sherry's question.
Okay. So Sherry says, how do you spell Vizier? Oh, let's go back to experimentation. Where's experiments? There it is. Vizier is V-I-Z-I-E-R. Sorry, I know that's probably maybe small again, but V-I-Z-I-E-R. Yes.
Perfect. Awesome. And then I think Salvador had a question. Also, are you able to share the link of that notebook with us? I wasn't able to find it.
Yeah, definitely. Let me go ahead and do that now. Let's see. Just want to make sure that we collapse all of it. I just need to edit it a little bit. So if you want to ask other questions, I can do that while we're.
Yeah. So Salvador asked, what are some Vertex alternatives and what are some of the considerations you look for using this tool versus something like AWS alternatives?
Yes. Okay. So, I mean, it's kind of a pick your poison type of thing, but there's kind of the considerations you want to have, right? Are if you're already using a cloud provider, it's probably easiest to continue to use that cloud provider because it's what you're familiar with, right? There's a lot of ramp up time involved when it comes to learning a new product, right? And if you already have some base knowledge about a cloud provider, if they're offering some sort of managed solution, in GCP's case, Vertex AI, in the case of Amazon, it would be, what do they call it? I can't remember. That's driving me crazy. That's going to drive me crazy. Someone get that and put it in the chat. It's really, no, not Athena. Talking about, I think on AWS. I'm going to get it right now. But the point is like if you're already familiar with something, just go with that, right? It's the easiest way. Now, if you're wanting to put together custom like MLOps solutions, right? My preferred method with anything really, always go for AWS, Sherry. So Amazon Web Services. SageMaker, Amazon SageMaker. Got it. All right, that was the AWS kind of version of Vertex AI. Yes. But when you're deciding on what to use, whether it's a library, a product, anything, you should always just try and find the most managed solution. This is my opinion, and people will disagree. But my opinion is go for the most managed thing that you can find. See how that works, right? And use it in a real business use case. Because that'll really you'll be able to poke holes and see exactly what works and exactly what doesn't for your company or your particular use case. Okay, if it works perfectly, great, you're done, right? But usually that's not the case. then you can start to back off and think, okay, what other products are solving this thing, and what would fit my use case better, right? There's lots of open source, there's lots of other paid products out there. So really it's a matter of deciding what's best for you, but you need to have a well-defined problem and a well-defined like a baseline to go from, right? It makes sense to do that, in my opinion, and it's less work. A lot of people, a lot of engineers have this in their head that they need to build things from scratch every time. I am literally the opposite. I am the laziest engineer, and I say, if it's already out there, why are you going to build it again, right? Just use it, right? Until you need to build something yourself, right? Because the real deal is in the real world at companies, they don't care how smart you are, right? I mean, they do, right? But they don't care like if you can build something from scratch. They want results, and the faster you can get those results, the better you'll look, right? And not only the better you'll look, but just the faster you'll get past certain problems, right? You don't want to sit there and spin your wheels on something that's already been solved. Okay, so always look for if there's a solution out there that'll solve your problem before you even start coding, right? Do a lot of research and just see what's going to be best for you.
Got it. I think Rowan has a question. Is there any limits on using GPUs and TPU?
Yeah, on Colab, there is a limit. You can't just unlimited use it. Now, side story, we used to use ngrok and hack into their, don't tell anybody, hack into their VM instances, and we'd use long-running processes to keep the instances alive so that the GPU would never die. And we'd basically hack GPUs and use them for like unlimited training. And that was years ago. They fixed that loophole, but we used to use JavaScript to run a process on their VM that's running in the background to keep that. But now there are limits. You cannot do that. It doesn't work anymore. And so, yes, there is also a premium service for Colab where you get unlimited GPU, TPU. Now, if you're talking about the cloud, of course, they charge for stuff, and it's per hour of use. So on GPUs, and that ranges from less than $1 per hour to all the way up to like tens of dollars per hour, I think, something like that, for the like really heavy duty GPUs.
And then another question on GPUs. Do you take advantage of the Colab GPUs?
Not so much anymore. And really the only reason is because, I mean, if I'm doing like running something like this, like where I'm maybe a lot of times when they come out with a paper or something, there'll be accompanying code. So many times I'll run that like in a Colab notebook if it's already like a Colab notebook that they have or whatever. But one thing that to note is, and I should have shown this, and I'll tell you why I didn't use this in just a second. I'm gonna reshare my screen for a second. Oop, no, go away. Oh crap. Hold on, give me one sec here. No, sorry. There. All right. I'm gonna share my screen real quick again, and I'll show you guys something here super quick. So one thing I didn't mention was GCP Workbench. So if you click into Workbench, these are actually also, oh, yeah, okay. So these are also notebooks. And so they actually have Jupyter notebooks, managed notebooks on GCP. Okay, so this is my company. So I was like, I'm going to do it out of Colab, just minimize my footprint on GCP. Not that my company cares, but just we deal with a lot of data that's like medical related. And so I don't want to open like an actual notebook and be showing stuff on just for the purpose of I don't want to accidentally show something I'm not supposed to. So I tried to work out of this Colab notebook as much as humanly possible. But nevertheless, you can actually work out of managed notebooks on here on GCP. And these notebooks actually have access to lots of different things on GCP. Like you can attach your GitHub repo. You can attach BigQuery and run BigQuery queries. If you know what BigQuery is, it's a highly scalable like SQL, or technically it's NoSQL. It's a columnar database. It's like the best product ever on GCP. Definitely check it out. BigQuery is the name of that. But really cool. So you could just work from within Vertex AI. Again, I worked from Colab because one, it's free, right? If you run a notebook on Vertex, you're paying for the compute. You pay for everything, right, on GCP, but also because of the reasons I mentioned before. So what was the original question? I forgot. Oh, I always work out of, right. No. So the answer, no, I don't always work out. Cool.
All right, great. Any other questions?
Well, Chris, I'm just curious if somebody wants to get set up quickly to start practicing and setting up like the models and that kind of thing.
Mm-hmm.
Where's a good place to get like data sets and that kind of stuff for practice?
Yeah, I mean, there's lots of places to get data sets. Here I can show you. Actually, we used a package, and it's called. Let me find it. I forget what it's called. Let's scoot down here and find it. TensorFlow data sets, something like that. So there's repositories in TensorFlow. If you're playing with TensorFlow specifically, it's really nice that the data set we use today, we actually got from Stanford. They have a huge repository of data sets, but TensorFlow has a lot of data sets, classic data sets built in that you can just access from their hub, their data set hub. There's and as well as models. So that's where we also got the models I forgot to mention is from TensorFlow Hub, right? And so TensorFlow data sets mixed with TensorFlow Hub, you already have models, you already have data, and you can just start, right? And if you're looking, TensorFlow has some great tutorials on how to use TensorFlow on their website from beginner to really advanced, and just some cool stuff like some of the newer stuff with text-defined pictures or whatever, where you tell it you want it to be in, a turtle in the style of Rembrandt, and it'll just it's a generative model that'll actually create a painting based on your text that you input. So you can play with a lot of these, and a lot of them are Colab notebooks. So you can just open them from the TensorFlow website in Colab and mess around, which is super fun. But data sets, Kaggle. So Kaggle is another very popular website, and they have a treasure trove of data sets on there. And you can also do competitions, data competitions.
Well, I can really see somebody getting into this and really going down a rabbit hole for a long time.
You're looking at a guy who has gone down the rabbit hole, continuing to fall as we speak.
Honey, dinner's ready.
All right. Well, thank you for answering all that question. Oh, by the way, were you able to get that link for the notebook?
For sure. Let me
and while you work on that, so thanks everyone for joining today's talk. But next week we'll have another talk. We're actually gonna have a talk on one of our graduates coming in talking about landing a job in the tech industry without years of experience. Here is the link where you can check it out and RSVP if you're interested. And then this is also recorded, and we'll be posting it on our YouTube channel later. And you can find that here on this Tech Talk playlist, and that will also have all the previous talks on there. And it looks like Chris also shared that link with the notebook, so check that out. But anyhow, thank you all for joining. Thank you so much, Chris, for another talk. We always enjoy it when you're joining us for these events. But I hope to see you guys next week, and have a good Friday.
Thank you, everybody.
Yeah, thanks, Chris. Great presentation as usual. Thank you.
Thank
Awesome.
you. Appreciate it. All right. Talk to y'all later.
Bye, guys. Bye.